Hello, and welcome to another URSA example. This is going to be a two-parter where we derive formulas for the fit parameters and their uncertainties in a least squares weighted linear regression model. So the idea of a linear regression model is that you collect a bunch of data, pairs of data points, and you think that there's a linear relationship between them, so you try to fit a linear model, which is of the form y equals b plus m times x. And that can be expressed using this formula. It says that yi, which is the ith y measurement, equals b plus m times xi, which is the ith x measurement, plus epsilon I, which is an error term. And that shows us how far off our model is. So b and m are the parameters, and we want to fit these such that the errors epsilon I are as close to zero as possible. So we're going to start by working with this formula and isolating the epsilon i's so that we can minimize the errors, and then we're going to plug that into a chi-squared equation and actually solve for b and m. So to isolate epsilon I on the one side of the equation, we basically need to subtract off the other terms, and that can be done with the rewrite rule equality.subtract, which you give a term and it subtracts that term from both sides of an equation. So I can say subtract b here, and b gets subtracted from both sides. Then I can say simplify, and that will cancel the plus b with the minus b on the right-hand side. And then I can say subtract m times index xi, which is index xi is x sub I, and then simplify again. And then we have something equals epsilon I. And then I can run the swap command to bring the epsilon I over to the left-hand side of the equality. So now epsilon I equals yi minus b times m times xi. And the prediction of our model is b plus m times x sub I. So subtracting that from the actual value gives us the error. So I'm going to save this equation as an equality called epsilon. And then I'm going to plug in the formula for the chi-squared value, which is the sum of the squares of the errors. And then I'm going to minimize that to find b and m. So the formula for chi-squared, I'm going to use some builder rules to build a new expression. I'm going to start with set. Builder.set used to be called expression.set. Now it's under the builder namespace. But I'm just going to plug in chi-squared here. This just sets the expression to whatever we plug in. And then I'm going to use reflexivity, which is under builder, which just replaces something with that thing equals itself. And then on the right-hand side, I'm going to use set again to plug in the definition of chi-squared, which is going to be the sum over all i's of the ith error squared divided by the ith uncertainty squared. So this is the definition of chi-squared. It's the sum of the squared errors divided by the sum of the squared uncertainties. And sigma I is basically the size of the error bar. So the smaller the error bar is, the more important that error is. So that's why we've divided these. And the error bars can be different from data point to data point, which is what makes this a weighted linear regression. So now I'm going to substitute in the value of epsilon. I named that epsilon earlier. So now we get the value of epsilon substituted in. And I'm going to name this now chi-squared. So I'm going to save this as an equality named chi-squared. And again, as I've discussed in earlier videos, when you use the /save command, the equations get saved under a table named equality. So both of those appear here now. So now I'm going to take some partial derivatives of chi-squared and solve for b and m. And in order to take a partial derivative, I'm going to just quickly show something first. When you take a partial derivative, you need to specify what parameters are held constant. And to motivate that, if I had a function, say f of x and y equals x plus y, that's all very nice. I can take partial derivatives, partial f partial x or partial f partial y. But what if I had some other variable like z equals 2x plus 3y? I could write f of x and z instead of f and x and y. And if I did that, then partial f partial x would really not be well defined, because f would have different definitions depending on whether I was considering it a function of f and of x and y or a function of x and z. So you need to specify which variables you're holding constant when you take a partial derivative. So going back over to this equation, we're going to take partial partial b and partial partial m of chi-squared. And in order to do that, we need to specify what chi-squared is a function of. And we can tell Ursa what that is by adding an entry to the function of table. So we're going to say that chi-squared is a function of b, m, x sub I for any I. That's what the underscore does. This is a pattern, and it will match anything. So this is now going to say that chi-squared is a function of these things: b, m, x sub I, y sub I, and sigma sub I for any I. So that, now that I've run it, it appears under function of. And this is not displaying properly, actually, but there it goes. It's telling me what I've declared chi-squared to be a function of. So now that we have this definition, I'm going to write down the two equations that we're going to set equal to 0 and use to solve for b and m. So I'm going to use builder.set again to just set chi-squared. I just want to see chi-squared, and then I'm going to use sequence.next to create another copy of chi-squared. And now I'm going to use builder.partialDerivative, which looks up the parameters from that function of table that we just added. So when I say partial derivative of b, it replaces chi-squared with partial partial b of chi-squared, and the partial derivative operator has the variable that you're taking the derivative with respect to, and it also has the list of parameters of the function. So this is partial partial b, where the function has this parameters. In other words, it's partial partial b where these parameters are held constant, everything except for b. And then we can do the same thing down here. We want to take the partial derivative with respect to m. Now for both of these, I'm going to use builder.reflexivity to create two copies. Set one side of the equality equal to 0. And now these are the two equations that we're going to solve and use to find expressions for b and m. So I'm going to go in here and substitute the definition of chi-squared that we had. And now we have two equations, and we can take these derivatives and solve for b and m. So we've got a system of two equations with two unknowns, b and m, and we're going to solve for that. So I can just use the derive rule now to take this partial derivative, and because it knows what's held constant, it's able to say that partial partial b of yi is 0, m is 0, and so on. And so it's able to solve this derivative pretty directly. And then I can use simplify to make that a little simpler. Now I'm going to clean up both of these a little bit more. The first thing that I'm going to do is we have a sum of the negative of the sum of a bunch of terms, and I'm going to use the distribute rule to distribute that negative inside of this sum and then simplify it. And then I'm going to distribute this negative inside and then simplify it. And now we have some coefficients of 2. And this appeared because we had a squared term that we took the derivative of, so a coefficient of 2 appeared. And we can divide that out by factoring out a 2, and then using equality.divide to divide both sides of the equation by 2, and then simplify, which cancels. Factor out a 2, divide by 2, and simplify. And now we want to solve for B and M, so we need to kind of isolate them. And I can do that by distributing this sigma sum over its argument. So distribute here takes this sum, this sigma sum of a bunch of terms and replaces it with a bunch of sums, sigma sums. And now I'd kind of like to pull this minus sign out as well. There are multiple ways to do that. I can use distribute, again, to distribute the sigma sum over the minus. I can also say commute neg to commute the neg, the unary negation out. Either way works. And I'll do the same thing down here. And also I'm going to swap x and y here, just to make that look a little nicer. Now we can also factor out b and m, because we're trying to solve for b and m, so we need to pull them out of the equation, or out so that they're kind of on their own. And they don't depend on I, so we can just use factor with b and factor with m to pull those out of the sigma sums. Factor b, factor m. And another thing that I'd like to do is move this first term over to the other side of the equality. Now we can use equality.add or equality.subtract to do that. Like equality.subtract 3 subtracts 3 from both sides of the equality. And I could type in this entire sigma sum, but there's an easier way to do it, which is we can use this rule called bind, which binds a pattern to the expression you have selected and allows you to plug parts of that expression into a rule. So if I say bind, we give it a pattern that it's going to bind this expression to. So I'm going to give it the pattern something equals something called a plus some more things. So this underscore is an anonymous pattern, and it just matches anything. And then this underscore a is a pattern, and it matches something and then calls it a. And then this underscore dot dot is another anonymous pattern that matches 0 or more arguments and just doesn't give them a name. So this expression that we have selected, which is 0 equals this term plus these two other terms, is going to match this, and this first sigma is going to get bound to a. So then we can say subtract a using the same equality.subtract rule, but a will get plugged in based on this match against our expression. So that subtracts that term from both sides. Then we can use simplify to cancel, and we can run the same rule down here and simplify to move that term over to the left-hand side. Now to make this look a little nicer, I'm going to give some of these sigma terms names. So I'm going to use the /name command, which assigns a variable name to whatever you have selected. I'm going to call this sy. The s stands for sum and the y stands for the numerator of this fraction, so I'm just going to call this one sy, then substitute. And then I'm going to call this s, and substitute. Substitute that. I'm going to call this one sy. SXY I meant. And this one's already called SX. This one I'm going to call SXX. Okay, so now this looks a little nicer. This is a system of equations with 2 equations and 2 unknowns, which we can solve. And there are some new rules which we can use to solve systems of equations like this. We can change this into a matrix equation, solve that, and then change it back to a system of equations. So if I use the 2 matrix equation rule, that will take this system of equations and change it into a matrix equation. So that does this. And again, just to show how that works, we have as the top equation sy equals b times s plus m times sx. And when I run 2 matrix equation, the top row has sy in the vector, and then the matrix here is sx as its top row, and it's multiplied by the vector bm. So when we multiply that through, the top row of this right-hand side is going to be b times s plus m times sx. So this matrix equation is the same thing as that system of equations we had earlier. So now, to solve this matrix equation and get the b and m vector on its own, we just need to multiply both sides by the inverse of this matrix. And in order not to have to type all that out, I'm going to use the bind rule again. So I'm going to bind my expression to something equals something applied to two things, which is a and something else. Or actually, I'll call this m for matrix. And so this, again, will pattern match the expression that we have selected. And it will bind the left-hand side to this anonymous variable. It will bind matrix multiply, this matrix multiplication operation, to this anonymous operator. It will bind the matrix to m, and then it will bind the vector anonymously. So now we have the matrix m. And we can now run the rule, Kong rule, which Kong rule takes a lambda expression like this one, and it applies that to both sides of an equality separately. So now, for my equality, I'm going to take the value on one side of the equality, and I'm going to replace it with the matrix multiplication of the inverse of m with whatever was on that side of the equation. So for each side of the equation, it's going to take that value on that side of the equation, and it's going to call that a, and it's going to replace it with matrix multiply of matrix inverse of m with a, where m is this matrix that we matched. So this is probably the most complicated rule that's going to be in this video, but when we run that, we get both sides multiplied by the matrix inverse. And now when I run simplify, this rule is smart enough to notice that it's got matrix inverse times the matrix, and it just cancels those out. So now we've got b and m on one side, and that's equal to this equation, or this expression on the other side. So now before we can convert this back from a system of equations, we need to compute this matrix inverse. And there's a rule called matrix inverse that computes 2 by 2 matrix inverses so far. So when we run this, it computes the inverse. And this actually now is a nested matrix multiply. This should show parentheses, but doesn't. But in any case, we need to simplify this so that it's a ternary matrix multiply operation. And that's okay because matrix multiplication is associative. So now we've got this equation for the vector b and m, and we can just do from matrix equation now to change this back to a system of equations. So I'm going to swap these equations and clean it up a little bit, clean both of these up. I'm going to swap the terms on the right-hand side to bring the numerator over the denominator, and then I'm going to actually call this delta. Name this delta. And then I will commute out the negative. Do a similar thing down here. Swap these terms, pull out a negative, and substitute delta. So now we've got formulas for b and m. These are the formulas, and we can write them in terms of all of our individual data points again. We can select each one of these and substitute its value back in. That's one way to do it. Substitute x, y. But there's actually a simpler way. Since we have this bind rule, we can just bind. Since I named the equations the same as the variables, we can just say bind underscore e in substitute e. And that will substitute the value of the variable. And that command can be used on any of these. And then we can also run that command top down to recursively substitute everything. And then we get all of the sigma sums just substituted in. But anyway, here are the equations for the variables, and in the next video I'm going to show how to calculate their uncertainties. See ya!